All right, continuing with our completely unedited videos, let's talk about Dalton's law of partial pressures. And essentially what Dalton's law of partial pressure says, if I have a volume of a mixture of gases, and let's just say this mixture of gases is air, that means that in this volume, the partial pressure of nitrogen, which is one of the components of air, will be exerted inside this volume as if it were by itself. And because nitrogen is 78% of the pressure of the atmosphere of air that exists at sea level, we can say that it's 0.78 atmospheres. We can, for oxygen, if let's just restrict our concentration of components in the air to just nitrogen and oxygen, we'll fudge the numbers a little bit and say that oxygen is 22%, which would mean that the partial pressure of oxygen is 0.22 atmospheres of pressure. So between the nitrogen and the oxygen, they're exerting a total of 1 atmosphere of pressure, each one of them exerting their own unique partial pressure. So we have 1 atmosphere of total pressure, which is just equal to the partial pressure of nitrogen, which is 0.78 atmospheres. And we're going to add the partial pressure of oxygen, which is 0.22 atmospheres. Okay, and just for accuracy's sake, we know that we have a partial pressure of water vapor. We have a partial pressure of carbon dioxide, about 0.03 atmospheres, and partial pressure of argon and a few trace gases. But that's the essence of Dalton's law of partial pressure. So let's go ahead and apply that to a real problem. So in this particular case, we're saying a mixture of hydrogen and helium is placed in a container, and that container is at 27 degrees Celsius, and it's a 1 liter container. So I have H2 in here, and I've got 1 gram of that stuff, and I've got 1 gram of helium in there. Well, if I'm going to use the ideal gas law, PV equals nRT, and I want to solve for the partial pressure of any one of those gases, I'm going to solve by taking the partial pressure of any one of those component gases is equal to nRT divided by the volume of the container. So in order to get the partial pressure, I need to go ahead and convert grams to moles. So moles of H2, my hydrogen, is going to equal, that's just going to equal 1 gram divided by the molar mass of hydrogen, 2.02, which equals 0.495 moles of H2. Moles of helium will simply be the 1 gram of helium I have divided by 4 grams per mole, which gives me 0.25 moles of helium. Okay, so if I plug that in for hydrogen, the partial pressure of hydrogen, that's the partial pressure of hydrogen, will equal 0.495 moles of hydrogen times 0.0821 times the temperature in Kelvin, which is 27 plus 273, which is 300 kelvins, divided by 1 liter of volume. And that's going to give me, it's going to give me 12.19 atmospheres. Okay, that's a 12.19 atmospheres. Remember, this is completely unedited. So let's go ahead and take the calculate the partial pressure of helium. That's going to be the 0.25 moles times 0.0821 liters atmospheres over moles Kelvin times 300 kelvins, and that again is divided by 1 liter. That's going to give us 6.16 atmospheres. So I can use Dalton's law of partial pressure to calculate the total pressure by simply taking the partial pressure of hydrogen, which is 12.19, plus the partial pressure of helium, which is 6.16. 0.16, which gives me 18.35 atmospheres of total pressure. All right, so let's go ahead and apply that using a concept known as the mole fraction. And here's what the mole fraction says. The mole fraction says that the pressure fraction, that is, if we're talking about hydrogen, the partial pressure of hydrogen divided by the total pressure in the container, in the volume of the container, is equal to the mole fraction. So this would be the mole fraction of hydrogen divided by the total number of moles. All right, so let's see if that's true. So for instance, the partial pressure of H2 we calculated as being 12.19 atmospheres. The total pressure that we calculated was 18.35 atmospheres, and that was just the combination of hydrogen and helium. So if I do a rough calculation of 12.19 divided by 18.35, I get 0.664. So my ratio is 0.664. Well, now what we're going to do is we're going to calculate the mole fraction of hydrogen divided by the total number of moles. Well, the number of moles of hydrogen that we calculated was 0.495 moles of hydrogen. That was simply 1 gram of hydrogen divided by the molar mass of hydrogen, which was 2.02. Now, the total number of moles will be the number of moles of hydrogen, which we calculated as 0.495, plus the number of moles of helium, which was 0.25. And if we add 0.495 to 0.25, we get a total number of moles of, it looks like, 0.745. So we're going to go ahead and calculate the mole fraction. So that's going to be 0.495 divided by 0.745. And again, we get 0.664 for our ratio. So it's true. The pressure fraction, this guy, the partial pressure of one component gas divided by the total pressure is equal to the mole fraction. And both of these guys are equal to 0.664. That's their ratio. So we can use that. If I happen to know what the mole fraction is, and I know what the total pressure is, or I can calculate it, I can calculate what in this case is the partial pressure of hydrogen based on the mole fraction of hydrogen, and I can do it right here. The partial pressure of H2 is equal to the mole fraction, which we calculated as 0.664, times the total pressure, which we calculated earlier as 18.35 atmospheres. So if I take 0.664 times 18.35, I get 12.19, which we did calculate as the partial pressure of hydrogen in that mixture of gases. So please use this ratio. The pressure fraction is equal to the mole fraction. To calculate the partial pressure of a gas is equal to the mole fraction of the gas times the total pressure to give you the partial pressure of the gas. All right, so let's just slide on by. We've done the strike anywhere matches problem. You're going to have one problem that is similar to that. That is going to be an extra credit problem on the exam, but I recommend you do it. It's worth some points to you. Let's talk about the connection between the ideal gas law and the atomic molecular level. And we use the kinetic molecular theory to go from the macroscopic level, where we calculate, or not calculate, but simply measure temperature, volume, and pressure, and to what's going on at the molecular level with respect to velocity, mass, and collisions. So here's what the kinetic molecular theory says. If I have gas particles that are sitting in a container, they are very, very small. They're so small that they're insignificant volume relative to the volume of the container they have. They're moving in continuous random motion. They're making contact. They're impacting the sides of the container, and they're also impacting each other. So they're constantly exchanging energy in what we call perfectly elastic collisions where no energy is lost. That's kinetic molecular theory of gases. What else is going on? Well, they're not doing any chemistry. They're just darting around as these particles of gas constantly impacting each other, the insides of the container. Now, what do we know about them also with respect to the absolute temperature? So all these particles, constant, random, chaotic motion, elastic collisions, exchanging energy, and the kinetic energy, the average kinetic energy is proportional to the absolute temperature. And so what we have here is that the kinetic energy proportional to the absolute temperature, and the kinetic energy is equal to 1/2 times the mass times the velocity squared. Now what happens if we increase the temperature? We increase the velocity. We're not going to change the mass, but we're going to increase the velocity, and that's going to cause an increase in kinetic energy. What's that mean for ideas like pressure, measurable volumes like pressure? That means we're going to increase two things. The gas particles are moving faster, and if they're moving faster, we're going to get more impacts, more frequent collisions with the insides of the container, but also the particles are moving faster, so the kinetic energy of those collisions has also increased. So we have an increase in kinetic energy of the collisions. We also have an increase in the frequency of the collisions with with the inside of the container, and that means pressure goes up. Okay? All right. So there we go. That's the kinetic molecular theory of gases, guys. So you can read over that in your notes. One more idea. Well, actually a couple of ideas. What is an ideal gas? An ideal gas is one that follows all of those postulates of the kinetic molecular theory. Under specific conditions, gases become less ideal. That is, they start disobeying the kinetic molecular theory of gases. Two things that can cause that to happen. I squeeze those molecules so close together. I put them under much, much higher pressure. Now those molecules of gas are squeezed so close together that the attractive and repulsive forces are no longer negligible. They start reacting with each other, and they become less ideal. They are attracted and repulsed by each other. So that's one way which you can deviate from ideal gas behavior to put gases under high pressures. The other thing you can do is you can cool the temperature down. You can reduce the temperature so much that those gas particles really start relating to each other. Those attractive and repulsive forces again start to interact with each other, and that's quite frankly how you get liquid nitrogen. Nitrogen is a gas under normal, ideal conditions. It's a gas. But if you cool it down or put it under enough pressure, then those molecules of gas start attracting each other and you get a liquid phase. Okay? Same thing happens. You cool them down, you put them under high pressure, you get non-ideal gas behavior. All right. So gas will behave most ideally under what sort of conditions? That would be low pressure and high temperature. Most ideal behavior is at low pressure, high temperature. Most non-ideal behavior would be under high pressure and low temperature. So high pressure, low temperature would be This would be indicating, all right, let's get out of this. This would be non-ideal, high pressure and low temperature. And by the way, non-ideal is known as real gas behavior. So non-ideal means real gas behavior. Ideal gas behavior happens under low pressure and high temperature. And that's just the way you normally think that gases work. So real gas, high pressure, low temperature. Ideal gas, low pressure, high temperature. All right, let's talk about effusion and diffusion. Last thing we're going to do. Effusion, as you remember, is the escape of molecules of gas through a tiny hole. Diffusion is just the spread of one substance throughout the space of another or second substance. So I open up the bottle of perfume for diffusion. It takes a while to get through all of the particles of air, oxygen, nitrogen, carbon dioxide, etc. And effusion looks like this. Effusion is just the number of particles of gas that can get through a tiny hole. And what you want to remember about this is that the kinetic energy is equal to 1/2 times the mass times the velocity squared. So the heavier the gas, the slower the velocity. The lighter the gas, the higher the velocity. And the higher the velocity, the more shots that get taken at the little tiny pores that exist in a container. And the more shots that a gas particle takes at the hole in a container, the more times it's going to get through from pure probability point of view. So the rate of effusion is going to be inversely proportional to its molar mass. So what that means is the lighter the gas, will have higher rates of effusion. Okay? So if I give you a collection of gases, as I did in this particular problem, you've got ammonia, and ammonia about 17.04 grams per mole. Let's see, methane about 16.05 grams per mole. I think argon's around 40 grams per mole. HBr is quite a bit heavier. Hydrogen chloride, I think this is about 80 grams per mole. And hydrogen chloride about 36.45 grams per mole. So if I were to arrange these in order from smallest, or let's say lowest effusion rate to highest effusion rate. So this would be the fastest gas, and it would also be the lightest gas. So that would be arranged as CH4, that would be the fastest rate of effusion. Then you'd have NH3, that would be next fastest. And then you would have, let's see, looks like HCl. HCl would be right down here. Argon would be a little bit slower at 40 grams per mole. And the slowest rate of effusion would be HBr. And that's going from lowest to highest rate of effusion.